Thanks very much. You did mention that I was working at Dana Corporation. It's an auto parts manufacturer in Halton region. It's in Oakville and in the Golden Horseshoe. So it's very good to have the participation of those two organizations that represent the manufacturing base in our area. The relationship with McMaster, it started quite a while ago. I moved to Natural Resources Canada. The federal lab moved from Ottawa to Hamilton. And McMaster, the relationship with McMaster is at least 10 to 15 years in the making. They were one of the key participants in getting the Ottawa lab to move. It happens that they presented a good case, and I think it worked extremely well in terms of being at the McMaster Innovation Park. And it's through McMaster that we've done work with Italian teams in different groups. So this is another example of that important relationship that we're here for. I want to talk about innovation and collaboration. So I'm going to shift a little bit. And I do have some information on the types of innovation that we work on. Of course, it's going to be tailored a bit to the automotive because I'm the program manager for materials in transportation. But we also work, because we're a federal lab, on pipeline materials, nuclear materials. We heard from John Luigi on the nuclear materials as well. So they're all very important to Canada. This is just one facet of an area that we want to study, and there's a reason for it. My presentation really should have said collaboration and innovation, because it started with collaboration like 15 years ago with McMaster, and for many, many years with universities. So in terms of nut planning, now I see the difficulty. I'm going to have to look up here. So the outline, I want to set the stage a little bit for the collaboration. And not everybody's talking about that, but that's a really important part of what made the automotive and the materials development in automotive so important. Not so important, but it made it really prosper in terms of us achieving things as a network. And so I'm going to talk about the national and international context, partly because I work with the government and looking at the whole cross-section of the network is important. And then lead into how we get to the innovation collaboratively. So Canada's manufacturing sector, why is it important? First of all, in the economy, $71 billion in revenues, $53 billion in exports in 2011. That went up by $10 billion within a year. Capital investment, $3 billion a year from 2002 to 2011. Manufacturing sees a lot of investment, and therefore there's a lot of activity around it. There's opportunities both in Canada and outside. The government recognizes that and sees things like employment, 109,000 people, and this is just in the automotive. With 332,000, I think, Anita, you were mentioning some leveraging numbers earlier. Somebody was mentioning some leveraging numbers. But that kind of activity, level of employment activity, is extremely important to the manufacturing base to realize when we have assembly plants, etc., parts manufacturers, tier 1 parts manufacturers, we're employing lots of people, and the spin-off of that is massive. In terms of the environment, one of the things that we have to realize is that transportation accounts for 24% of GHGs. There's a massive amount of CO2 that's generated in the automotive from the use of vehicles, but also from the manufacturing. So getting those processes to be more effective and better at more energy efficient is an important part of it. It accounts for 22% of potential emissions reductions. Right now, with the initiatives that we have to focus a great deal on what's happening in the automotive, because we have great potential to make an impact moving forward. If we stop and think about where the regulations came from, the regulations for the CAFE standards came about simply because they recognized the potential. They also looked at, and talking about megatrends from this morning, thanks by the way, the megatrends from this morning, we realized that the environmental impacts are important. We also know that we have enabling technologies or need to develop those enabling technologies so we can get to the point where in 2025 we can actually hit the CAFE standards. Right now, 97% of vehicles are powered by petroleum. It's a huge number. There's lots to be said about electrification. McMaster has a great initiative on electrification, but we're still not there in terms of the market penetration we need so that we can really reduce the CO2. So, the automotive industry R&D investment, the industry R&D alone was measured by Industry Canada at $460 million on average over the years 2002 to 2011. It's a massive, massive investment in R&D. The direct investment by Industry Canada also to the automotive innovation. The Automotive Innovation Fund, we've seen a couple rounds of that now. There's another round now where there's money being invested. That money targets investment in companies like Magna's taken advantage of it before, Toyota. Ford Motor Company recently announced an investment in their assembly plant in Oakville. So major infrastructure, that's why the dollars are so large. But part of that is to make sure that we're actually looking at investment by those companies in R&D. So that's one of the fallouts of those types of investments. And it's because of those things about the value generation, the amount that it generates in terms of employment, that it's important for us to be doing some stuff like this. There's an NSERC program, Automotive Partnership Canada, that invested $145 million. And that's not each year, but that's a one-time allocation. And I'm going to talk about that in the context of collaboration as I move through the slides. Another network, Auto 21, and the networks of centers of excellence, it invested $81 million over the period 2001 to 2013. There's still ongoing activities associated with that, but that's again a very large, substantial amount of money that's going into investment in the types of technologies that are actually going to allow us to achieve what we want. I mentioned the Natural Science and Engineering Research Council. There's other activities that they invest in. NSERC spends about $1 billion or more on research. Now that's broadly right across the country in all areas, all sectors, all activities. I don't have the specific numbers for what actually gets into automotive research, but I participate on the panels, like the strategic project panels, the collaborative R&D research proposals. I participate in evaluating those at times. I look at the different technologies that are out there. So I have a very great position to be able to see all the different activities that are going on within the network through participation in things like that. The Ontario Research Fund, it's not just the federal government that's investing. The Ontario Research Fund, which is sponsored the IMI program with Waterloo and McMaster, invested on the order of $15 million. And I think that that's right. It started in about 2006 and is finishing up soon. Right, Nick? So again, there's significant investment. The National Research Council also reports about $35 million a year in the type of work that they're doing on materials research. They focus a lot on aluminum technology. They've got a center in Chicoutimi in Quebec, which is close to the aluminum industry, and therefore they're closely linked with that. They also have a polymer composite technology center in Concord, which is closer to us here. Transport Canada and Environment Canada are also very interested in the type of work we do, because we're helping them to succeed in meeting the goals of GHG, which is important to Environment Canada. And Transport Canada really cares about safety of vehicles. And I'll show a couple examples where it's important to understand that all these players are participating in how we got to the point of being able to collaborate as a group. Natural Resources Canada. So when we moved from Ottawa, the building that's shown here is the new facility in Hamilton. It's on McMaster Innovation Park. We have a few more trees, I think, now than we did before. It's a little bit nicer, but that's a picture of the lab. The one important part, though the lab is set up in virtually all aspects of metallurgical research is there, and we do have some ceramics that match up with some of the work that we saw earlier. But the important part of the lab is this section right back in here. It's a pilot scale facility, and there's much of the investment that we put in. We put in about $43 million in new capital in moving to this facility so that we could service the local area, the local industry, and broadly across Canada very well with equipment that you wouldn't necessarily be able to invest in if you were a private company, especially a small company. And it's pilot scale equipment, so we're able to run a lot of, we could run actual production parts, not production parts, we could run prototype parts or experimental parts on equipment that's scaled to the size that you would see in industry at any given time. The funding that we get, the core funding that we get, so in terms of the numbers that we directly get from the government, we get $4.8 million in automotive research. It's very small in terms of that total picture of what we see of investment in Canada. Yet, we are expected as a group of 100 people to really take and move forward the innovative materials using that capital infrastructure that we have as efficiently as possible to make sure that we achieve the goals of the government, but also of industry in terms of the lightweighting and the energy efficiency and GHG reduction that we talked about earlier. So we get funding from programs like the Eco Energy Innovation Initiative, the Program on Energy R&D. That's done through Natural Resources Canada, and of course our core investment. They give us a certain amount of money to run the program. Of the $4.8 million, we probably get, in terms of industry contribution, on the order of $500,000 of cash into the program, and that's changing rapidly as we, being located in the heart of manufacturing here, we're now engaging more and more, and we're getting a lot of investment to try and do research. So these programs here provide about $1 million, and about $1.5 million, so $3.5 million. And then there's some other sources of income for the automotive program itself. But it's small. What it forces us to do is get involved much, much more in collaborative research. And that's really where I want to go. All these investments are just setting up over many years, 10 and 15 years, are setting up our ability to work together as universities, as federal labs, and that includes both the National Research Council and Natural Resources Canada. Excuse me. There's also an international context to this, and though this event is an example of that, there's a few initiatives and a few relationships that we've developed that are extremely important to us. We realize that we are a fairly small player in the North American context and within the global context. So one of the things that we've done is align very well with the Vehicle Technologies Office and Materials Technology specifically in the U.S. Department of Energy. The Prime Minister and the President identified an opportunity for us to work together on clean energy. And so transportation plays a role in clean energy. One of the initiatives that was funded in the U.S. and in Canada is the Multimaterial Light Vehicle. And I'll talk a little bit about what that is and why it's important. It's fairly obvious. The light materials, getting the vehicle weight down is an important initiative. Using multi-materials to get it is something that they've recognized as an important contribution. We also participate in the International Energy Agency, the implementing agreement on advanced materials for transportation. That basically is a network of countries that joins a given implementing agreement and allows you to work collaboratively on research of interest to that country participating. So there's, I think, 7 or 8 countries involved. You can participate in the kinds of materials research that you want. You do task sharing. So what happens is we'll do some work on a certain technology. There'll be another country, the US, perhaps one of the Chinese institutes, Israel, Germany, England. They're all participants in the International Energy Agency, but they get to choose which project is of most interest to them. And so that's a nice way to, first of all, get it in front of them so that you know what the different countries are working on, but also to work on the things that are important to your country or to your labs in your country. And that's an activity that I've been involved in over the last 4 years. Light Metals Alliance, for obvious reasons, we do a lot of work on metals research. There's 5 countries that are involved in the Light Metals Alliance, and it's a collaborative network to look at aluminum, magnesium, and titanium. Titanium is used so much in automotive, and for that matter, magnesium is only beginning to be used more in automotive. But it's these kinds of activities that look for opportunities to integrate those lightweight metals into high volume production. It's a little different than low volume. Academic institutions, the ones that we work with across the country, there's specific ones, of course, that work on automotive related work, but universities like British Columbia, UBC, École Polytechnique, McGill, McMaster, and they also have automotive related groups within their organizations that promote specific activities that we would be working on. We've got many researchers across the universities. There's 57 researchers in 21 academic institutions that are involved in the Auto 21 National Centers of Excellence. That activity is now winding up, and materials and manufacturing is one of the themes within the Auto 21 network that has delivered a great deal of value to industry itself, but also in establishing the type of network that is able to achieve the type of things that we need for energy efficiency. There's also an NRC network called Canmet, and that's to promote and understand magnesium alloys and promote their use, look for opportunities for where we can integrate magnesium in a meaningful way. There's 21 researchers and 5 academic institutions that are participating in that. Of course, the government labs I mentioned already, our lab, Canmet Materials in Hamilton, the National Research Council, of the many different institutes that they have across the country. These 4 are really the ones that participate in metals research, especially for automotive, the vehicle technology program. But we work with industrial research facilities, the raw material suppliers, the tiered supply base, and the original equipment manufacturers. So the network is made up of all the different researchers from universities, from industry, from the federal labs, and with funding. And somebody mentioned yesterday in some discussions, it really said, how do you get a network and collaboration started? You do it through the things that I talked about in the investments that the government's making, that industry is making. For every dollar in the program that I run, we get about 1.3 or so dollars of industry contribution to the projects, which is extremely high. I don't know if there's statistics elsewhere, but I would say it's very good in terms of the amount of leverage we're getting from the contribution of the industry itself. Okay, so now I'm going to move to the things that make a little bit more sense. What do we do with all of that? This is where I'd like to go next. Okay, so some of the trends. Fuel economy. Something that surprises people a great deal, and this is data from North America. So something that surprises, over a 20-year span, fuel economy barely changed. Yeah, we had the oil problems earlier, but it really didn't change. The transportation sector, however, accounts for 36% of energy use, 24% of GHG. Okay, huge numbers. That's just transportation. And a majority from petroleum fuels. So another thing, vehicle weight actually over that 20-year period increased by 10%. Why did it increase by 10%? It's because we want cars that go accelerate faster. We want cars that have more space. We want cars that are more technologically enabled, infotainment, etc. So in the fallback of this up to 2010, This is fairly stable. We're working diligently to lightweight a car, and everybody is familiar with that. The challenge, all it means now is that the challenge moving ahead is even greater because we still have to get the car lighter eventually. Another thing is what are we up against? The CAFE regulation and the equivalent for Canada is just in terms of GHGs, but we have to hit a 54.5 mile per gallon target. And how do we get there? So we have to get there through lightweighting materials, powertrain efficiency. There's a number of different ways to do that, but materials is one of them. We have to make powertrains last, be able to survive higher pressures, higher temperatures, and to do that kind of thing, you could look in the direction of ceramics, as we learned earlier today, but you can also look at opportunities with metals, and that's what we do most at Canmet Materials. And, oh, I hit both. This, no, which way did I go? Sorry. Here we go. And the third way to look at this is that 70% of the energy from fuel, when you burn it, goes right out through the radiator and out the exhaust. So 70% of the energy is lost. So there's a great opportunity to both recover and convert that energy in one way or another. So I'm going to talk a little bit about an opportunity for that, for instance. Okay. So what are we trying to do? We're trying to make industry competitive. We want to get the environmental benefits while we're doing it. The problem is that whenever we go and we try and lightweight, we're going to have to do that without affecting the vehicle safety. So we still have to pass the crash tests. We still want people to know that they're safe. A lot of the things that we work on are things that improve the safety by actually making the intrusion distance. And I was mentioning it earlier, the intrusion distance on a crash, so that it doesn't actually get near you under the same circumstances of the vehicle before. There's another few important things here. Reliance on fossil fuels. If we're using less, we're better off. Reduce GHGs, everybody knows that. It's everywhere. Clean and renewable energy. We're working on materials that actually enable you to get electric vehicles working, which means you can get clean electricity. Key technical challenges, really manufacturing, strength of materials, durability of materials, and getting materials to do more things within the vehicle, not just the traditional materials. Who are we working with? Basically, raw material suppliers, the supply chain, vehicle assemblers. What are they looking for? Performance knowledge. That they need to do that simply because they need to reduce the risks associated with introducing new materials. You have to understand how new and novel materials behave so that you can actually integrate them into your products. One of the things we don't do is make products. What we do is hopefully enable the parts suppliers and the assembly people to be able to make the products and the vehicles that we talked about today. Who do we work with? One of the mechanisms that we identified earlier was that there's some key universities that we have collaborative research agreements with. McMaster was the first university for us to join, and it's because of that long-standing relationship that we actually probably entered into that agreement, and with the transition to the Hamilton area, it just made sense for us to work together. Here's 7 projects. Again, we're 100 people with a small investment in a lab that's very focused on metals research. And what we realized is that without collaboration, we weren't going to be able to achieve the things that we wanted to achieve. So Automotive Partnership Canada, one of the funding organizations, $145 million spent. There's 7 projects that we're involved in, and it's very diverse. There's magnesium here, there's aluminum and high-strength steels here, aluminum casting with McMaster. Sumant Shankar is one of the partners here. These are looking at extruded front rails, aluminum alloys, and this is a project on lithium iron phosphate we heard from Gianluigi earlier, that there's battery materials that they're looking at. Well, this is a material that goes into the electrodes of lithium-ion cells. Sorry, here. This is a material that's used in that. And so we're involved in that. The reason that we're involved in all these projects is that we have some expertise, either researchers, or we have equipment that can be used very effectively, which they don't have. And so we're an integral part in delivering that. We're a small group of 100 people, 75 technical, 37 PhDs, and we're working with a broad base of universities and people to be able to enable them to achieve what they want to do. So now into a little bit more of the details of what we do. We saw three things that were important. Vehicle lightweighting. So by 2025, and I was involved in 2011 in a workshop put on by the US DOE. They had 350 people from industry, academia, and from the federal labs in both Canada and the United States. There were probably a few international participants as well. And some of the stuff that they recognized is that to achieve the fuel economy goals, these are the kinds of targets we are going to have to take. Take the body structure and reduce the weight by 50% by 2025. We don't have a lot of time to do that, and if you stop and think about how do we even integrate those technologies into vehicles when they only change every so many years. The models change. It's very hard to get these kinds of targets. But this is what they felt was a stretch goal, but possible, but also necessary to get to where we wanted to go. Some of the stuff that we're working on is we're casting in a high-pressure die caster a magnesium alloy, and it's AM50 or AM60. I'm trying to remember which, but this magnesium structure sits right beside the wheel, and it holds the rails, the crush rails. When you get into a crash, the crush rails are held by this structure, and the wheel sits right beside it, and the shock absorber, which allows your car to go up and down, sits right in here. One of the things that we have is a 1,200-ton press, and I'm not spending a lot of time all the facilities because it's best to just come and see them. But we have a 1,200-ton high-pressure die casting press that allows us to make these kinds of parts. We made 400 parts in a single run that fed a three-country collaboration between the United States, Canada, and China, because they have great interest in magnesium, of course, because they make most of the magnesium globally. And so we have a three-country collaboration where each country is taking the parts that we've manufactured on our press and use them for their studies. One might be doing strength, one might be doing durability, one's doing corrosion, etc. And so that type of collaboration allows us to pull a team together. And this is about a $3 to $4 million a year activity. Our investment's about $200,000 to be able to generate the kind of parts that go in. Very important to be able to have the parts for this kind of activity. And so putting that amount of investment into the equipment that we have is critical to the success of that kind of research. Carrying on with lightweighting, I mentioned the multi-material vehicle. Well, structures traditionally have been made out of steel, so mild steels, high-strength, low-alloy steels. There's increasing pressure to take the vehicles and make them out of, well, mild steels, high-strength steels, but also advanced high-strength steels, extremely high-strength steels. These steels put on the same vehicle pose a challenge in that you have to be able to join these high-strength steels to steel. There's other opportunities where we could take the example of the magnesium part that I showed you is also made in aluminum, and we actually have that part in production in vehicles out of aluminum. The problem that comes up is, how do I join them? So if I had to join aluminum or magnesium, a casting to a sheet metal of different materials. Sometimes it's within the alloy itself, aluminum alloy to another aluminum alloy, and I can't actually weld them using the traditional methods. Well, there's a method that we're looking at is friction stir spot welding. The reason that we're very interested in friction stir spot welding is that the method basically takes two pieces of metal, and you put them, overlap them together, And in a traditional sense, we would take and we'd see the spot welders. In automotive assembly, we see spot welders. It's always exciting because it spits out metal and it's hot and it's interesting in terms of seeing a car actually being made in an assembly line. The idea here is that you can take the robots and the infrastructure that you have. You don't have to actually buy new equipment. You use that equipment, you put a new head on, and you go in and you take a tool, much like a drill bit, you drive it into the metal, but you don't melt it. And if you don't melt that metal, then you can create a joint or a spot weld, friction stir spot weld, and we're looking at that technology. This is a special approach to it, where if I took a traditional friction stir spot welder, I would be left with a drill hole, because there's a drill that went in there and mixed those two metals together. And what they do is they actually drill, and then the metal pushes back up on the edges, and then they drive that metal back in, and then they get a flat surface. A sample or a joint with a big hole in it is just likely going to be much weaker and likely going to fall apart by fatigue in the service life of the vehicle. So we're studying how to join things like aluminum to steel, high-strength steel, magnesium to aluminum, aluminum sheet metal to aluminum castings, those kinds of things. And this is a cross-section of what that joint looks like. Normally, you'd see it, it would have a large hole right here because of the drill bit itself. So we're studying that. This is a collaboration that we have with Magna Corporation, and University of Waterloo has one of these heads, which allows us to do some studying. In terms of lightweighting, everybody realizes, of course, you can apply aluminum and magnesium alloys to lightweighting, but we've also are focusing a great deal on advanced high-strength steels. So very high-strength steels. And one of the things that goes with high-strength steels is that if I try and take a part that would, like a frame, a B-pillar or an A-pillar, that's what protects you up and around your head in a vehicle. If you take that and look at a traditional manufacturing method, they would take a tube and they would hydroform that tube into a shape. And that's what protects you from rollover, crash, that kind of thing. What we're doing here is we're looking at the high-strength steels and saying, if I take that high-strength steel and expand it out in a hydroforming press, and then I relieve the pressure, it shrinks back. And then predicting the shape of that part, it gets extremely difficult. So we're working right now with Veriform, who's a hydroforming company that makes those kinds of parts, and we're looking at the spring back of these steel tubes that get bent into the shapes that would protect us in a car. And what we realized very early is that there's some problems with making a tube out of flat sheet, rolling it up, you get residual stress. And that residual stress, and then I hydroform, it's extremely hard to predict what's going on. So we're doing some experiments, but also computation to be able to predict how to get the right shape at the end. And that's important. The number one thing that causes a part, well, a major thing that causes a part not to get deployed into production is the cost of the tooling to develop it. Not only the production tooling, but the prototype tooling. If we can get a good idea of how springback behaves in this, we can cut it back significantly to the point where we might be able to have one tool that hits the shape, and then we go right into a production scenario. And that's an important contribution. Further on lightweighting, about 50% of the activity in Canmet is actually on lightweighting, so I've given a lot of examples here. This one is a GM technology. I talked about spot welding, traditional spot welding, where they literally arc it together. This is a spot weld between two different metals. You've got a sheet material, aluminum sheet material here, and a aluminum casting. Very different materials. Normally, that would form brittle structures in here if you can't control the conditions very well. What GM found and patented was a method for that spot welding. The problem was, it wasn't that they couldn't get the process to work, they got the patent on the process. The problem was, they didn't know how strong the joint was in the spot weld, and so they couldn't predict exactly how it was going to behave when they designed the vehicle that might compete with, say, the Ford F-150, right? The Ford F-150 truck is now an all-aluminum vehicle, and they're looking at, GM is looking at the opportunity to do that and deploy it in other vehicles as well. The point here is that Canmet developed a technique, this testing technique, which is now an ASTM standard, that allows you to predict the actual behavior of that nugget. Oops, back again. Of that nugget. And being able to do that allows GM now to take and design that next vehicle much more reliably. The interesting thing is, each time they pull, they do different combinations of metals, and we can tell exactly how they're going to behave. Something that we do as well is computational work. This one was looking at third generation steel, so trying to find extremely strong, tough. So ductile and strong makes a very tough material. So these third generation steels, we know through our work with the U.S. Department of Energy that they have a massive initiative. They'd be spending tens of millions of dollars on this kind of activity. But we found out through close discussions with them that they had a gap in one of the areas where computationally they weren't addressing what they needed to be able to do computational materials engineering, literally to design those steels. Making every steel at Canmet is not the most cost-effective way of doing it. So using computational means is a way to do this. So virtual microstructure. We've seen a number of cases. Gianluigi showed us some stuff on the grain structure in materials. So we've got a typical microstructure here. They're taking the microstructure and developing codes that allow us to do yield curves, so how a material plastically deforms, and looking at forming limit curves, all through computation. And if you can take a chemistry, look at the grain structure that's created, get Gianluigi to tell us exactly what that grain structure is if we ever have to make an alloy, but computationally do 10 different versions before we make a single cast. We can go predict how it's going to behave and how it's going to form, and we'll be able to tell whether it can serve our needs to form a large panel for the front of your vehicle, for instance. So computational means is another area. On the powertrain, because I did focus a lot on the lightweighting, on the powertrain, there's things like manifolds. Our manifolds, if we wanted to run more efficiently, we have to handle higher temperatures, higher pressures. To do that, you have to get manifolds that can actually handle that. In collaboration with McMaster, with Stephen Velthus at McMaster, we created an alloy that we felt was going to be more effective in terms of balancing the high temperature strength with the machinability and the manufacturability. You have to do those things, otherwise you can't get to where you want to be. So trigger happy. The H-bars here are set up so that we do machining studies, and then we take the cast parts, cut samples out, and look at the oxidation and the high temperature behavior of them. So we're developing those. Why do we need that? By 2025, exhaust temperatures are going to rise by 80 degrees. Look at the temperatures here. Earlier we heard 1,000 degrees, 600 degrees, those kinds of numbers. That's the kind of number that we have to deal with in terms of what's going on. Block temperatures, so our aluminum blocks, our aluminum engines have to survive temperatures greater than 200, 250 is the target. Pressures are going up. If we try and get these materials into diesel applications, diesel even runs higher pressures. So these are the kinds of challenges that we have to do. Sorry, I missed it when I started the slide. Another approach on the powertrain is to do electrical steels. Not every vehicle in the future is going to be made from a traditional internal combustion engine. In fact, if we could switch it over to the electrical vehicles, we'd be advancing a lot faster on the GHG front. But one of the things that we're working on right now is a way of rolling materials so that you can make motors and get the right texture, or the right crystal structure and orientation, so that you get very effective electromagnetic behavior in the electric motor. So we're working on those materials to enhance our ability to get to efficient powertrains. the last example that I have here, that's 70% of the heat that gets lost in combustion, from combustion in a vehicle. As I raise temperature, it gets worse. I still have to deal with the heat. We're going to see a lot more turbocharging as we move forward, and that poses some problems in terms of dealing with the temperatures, higher temperatures as well, and of course batteries. So there's lots of aspects around heat and energy management that we have to deal with in terms of those materials. One example is thermoelectrics. At Canmet right now, and they're collaborating with the US DOE and at least one of the national labs in the US through the International Energy Agency with a few different universities, Toronto, Waterloo, McMaster. All of that group is now coming together to be able to develop a material that takes heat, converts it to electricity, so we can charge a battery. And that's an example of exhaust heat recovery. We're doing it right from the atom structure, and Gianluigi gave us a good idea of looking at atoms. Well, these guys are doing calculations and trying to figure out exactly what the material needs to be so that we can understand more about how it behaves in a thermoelectric generator. And then we have companies, the company I work for, Dana, who is a heat exchanger manufacturer, really focusing on recovering that heat through a heat exchanger and converting it to electricity. So another contribution. Every one of the projects is a massive leveraging and collaboration with universities with expertise around Canada and to some extent around the world to be able to understand what we should be working on and how we're doing it. So we're doing good things with materials, and it's through that collaboration that we're achieving the kinds of things that we need to achieve to reach the goals. That's it.